guys, welcome to Makeshift. This is our first inaugural video. Our first project that we're going to be working on. You can see the parts out in front of us. That's right, we're going to take a look at building a homemade DIY CNC machine. Since we're going to be doing a lot of digital fabrication in future projects, I couldn't think of a better project to start with. So as you can see, I've already started to fabricate a lot of the parts. We've got things that have been cut on the metal saw, we've got things that have been 3D printed, we've got parts that have been laser cut, and you're thinking already, how am I going to be able to make these things? I don't have a laser cutter, I don't have a 3D printer. Well, the key is very simple. Go find your local makerspace. These tools are readily accessible. You just have to do a little bit of research to figure out where locally you can find them. Alright, so where do we begin? We've got all of these parts. What we want to do is break this up into segments, and we're going to talk about some of the design exercises that I went through to problem solve the components of the CNC router. I'm going to go into more depth about the decision making that I went through and the learning process that I went through as I was making this, so that you guys can design your own CNC with the tools and the materials that you have available to you. So why don't we take this inside and get out of this damn Texas heat. Okay, now that we're a little bit more comfortable, let's take a look at some of the parts for the base and a portion of the gantry system. We've got our two verticals for the gantry that are already partially assembled with the rolling system. We've got our horizontal cross member that goes on the bottom of our gantry system and will capture our lead nut screw for our X-axis. We've got a few T-slot extrusions. These are 40-80 T-slot extrusions. These will be the main rails for the X-axis. We've also got our main X-axis control system, which include the front and the rear panels, and our main lead screw connected to a NEMA 23 motor. And you can see the lead screw nut that's on there that will be connected to this bottom horizontal cross member. We've got a few smaller T-slot extrusions here that will be the rails that support our bed or our wasteboard, which is right here. You can see I've already drilled the holes and inserted a few inserts that are hammer in. These will be used for clamps to clamp our materials. The great thing about this is, I've got 12 of them in here, but I'll probably need more in the future, so I can always take this wasteboard off, drill a few new holes, and add a few new threaded inserts for clamps. Those are the main parts for the base and the bottom portion of the gantry system, so let's get started building it. Okay, first off, what we're going to do is we're going to take a look at the gantry system and how that kind of functions. You can see on the verticals I've already assembled the roller system. Now what the roller system is made up of is a spacer with a roller bearing there. This is just a typical skate bearing. I've got a small little washer in there that you can see. Then I've got this acrylic wheel, and then a lock nut that's on a hex screw that goes through the entire system. Getting to this point actually took quite a bit of time. Using the slot as a way to index that gantry along the rail was really important to me, and I used that as a starting point when designing the roller system. And as you can see here, I went through several different wheel designs. Several of them were 3D printed and captured the bearing inside the wheel, and the wheel sat in the slot and rolled pretty well. I realized that the resolution of 3D printing didn't create a very smooth wheel, and so there was some jittering along the rotation, but otherwise a pretty good system. I've made several iterations of that. I laser cut a wheel that had the bearing embedded, and that system worked all right, but it didn't roll well in the slot itself. And I think part of that is because when you had a wheel that was as wide as the slot was, the laser actually is tapered, and so it's focused at a certain point, but on either side of that focus point the laser expands in either direction. And what that causes, if you look really close, is there's a slight taperedness to the wheel itself. So the wheel wasn't straight up perpendicular to that slot. It was actually slightly canted, which caused a little bit of binding. So that system didn't work. I tried CNC routing a wheel that captured the bearing as well. You can see in this particular wheel, the bearing sat inside there, and then the wheel rolled along the slot kind of like that, and that flange is what resisted lateral motion by kind of locking into that slot. That was great, except for one small aspect, which was at the starting point of each layer of cutting that the CNC router did, there was it created a small inconsistency in the wheel. It was a small little flat spot. And so you could see that as it was rolling, it would roll really smooth and then it would kind of hesitate and roll and then hesitate. And so this wasn't a great method either. So what I ultimately ended up coming up with is I just needed something that would act as a guide and resist lateral motion. It didn't need to be smooth, it just needed to fit in the slot snugly. And the wheel I knew was perfectly concentric and perfectly smooth, or the bearing I mean, was perfectly concentric and perfectly smooth. And so if I could use the bearing on the main surface of the slot here, and then have some kind of guide that would fit inside the slot, as long as everything was spaced exactly right and very low tolerances, then I would have a system that would run smoothly and still resist lateral motion. And the way that I was able to accomplish that low tolerance was by creating these custom spacers. Acrylic isn't completely flat, so even though I had a piece of 3/8 inch acrylic, it wasn't perfectly 3/8 inch all the way across. It actually sloped from one side to the other of the piece of acrylic I had. One side was thinner, one side was fatter. And I created essentially a series of spacers that were slightly different thicknesses. I assembled the gantry system on the rails, set at the right width for the table, and figured out which spacer allowed for a snug fit so that guide wheel was snug against that rail. When it was on the rail in there, it didn't allow for any motion when you had the other rail on there as well. That's how I created the exact right spacer that had kind of the tolerance of lateral motion that was acceptable, which is pretty much nothing. So that's the wheel assembly. I've already got these assembled for both of the verticals. The next thing that we need to do is we need to go ahead and add the bottom horizontal cross member. What we need to take a look at first is this T-slot. Now, I should preface with saying that this T-slot extrusion that I'm using for this project is something I had on hand. It was left over from another project. I think if I were to do this again, I probably would go with an open builds T-slot or a V-slot system that has a lot of accessories and wheels and all kinds of things that allow for linear motion a lot more easy. This system required a lot of trial and error to get right, and I don't think it's the best system, but it's what I had on hand, so that's what I used. And if you look at the end profile of this T-slot, you can see that we have these two holes here. Those are what I'm going to use to mount the verticals to. So what I had to do is I had to get a 7/16 tap, and I got 7/16 inch bolts, and I threaded those 4 holes on either side. One thing to note is that in this particular extrusion, those holes are not just a perfect hole. It's actually kind of a star shaped. And so because of that, the threads are not consistent all the way around. They have little breaks in them, which makes them slightly weaker. What I'm going to do is I'm going to add a little bit of removable Loctite to the bolts as I assemble it to make sure that those threads lock in and they don't eventually come loose. Okay? So let's get started. got the base of the gantry more or less assembled, what we're going to want to do now is add our T-slot extrusions to the side. These are the main T-slot rails for the X-axis. Very simply, we just want to slide them on. And the goal with this is to make sure that there's no binding, that they roll smoothly, there's no play. And it looks like we've got a little bit of binding here. Okay, so we just identified a new issue that I hadn't encountered before. These washers that hold that horizontal cross member for the gantry on are just a little bit too thick. The tolerances between the side of the gantry and the rails cause those washers to scrape along the rails as I'm inserting the rails. So what I'm going to do is I'm just going to shave off the top of those washers. Okay, we've made the adjustments to the washers. You can see we took the top half off of the washer there so that the bearings are slightly above any surfaces along here and the rails won't hit these. So we'll see how they fit. And we'll just slide these right through there. Oh, like butter. Okay, one thing to mention about this design is that most of your T-slot is going to be in metric. So in this case, these are 40-80 T-slot extrusions. You can find 20-40, you can find 40-40, you can find all different sizes. But what that means is that this is 80 millimeters tall. These bearings, which are 608 R2S, or excuse me, 2RS bearings, are 22 millimeters tall. So if you know that you want the center of your hole to be half of the diameter of the bearing off the top, and you want the center of the bottom hole to be half the diameter of the bearing off the bottom, you know that the distance between your hole to hole of these 2 points here are going to be the diameter of the bearing plus the height of your extrusion. In this case, it's going to be 102 millimeters. Another thing is with those 608 bearings, there's several different kinds of 608 skate bearings. There's 608Z, there's 608RS, there's 608 2RS. The reason I went with 2RS is what that means is two-side rubber seal. 608Z bearing has a metal surface on one side of the bearing. An RS bearing has a rubber seal on one side of the bearing, and the 2RS has a rubber seal on both sides of the bearing. This is really important for us because it makes the bearings maintenance free. Because they've got a rubber seal on both sides, the bearings become sealed, they don't need lubrication, they're not going to wear out as quick, especially in an environment with lots of dust and debris like you'd get with a CNC router. Okay, for the assembly of the base, we've got our two end pieces here. This will be the front, this is going to be the back, so that the motor's on the back side. We've got our two T-slot extrusions that will be the rails that hold the bed. And then we've got 8 of our 7/16" bolts and washers that we'll use a little bit of thread locker on to hold the front and the back together. Alright, as we start to do the final assembly of the base, let's talk about the X-axis drive system here. So as you can see, I already have it assembled, and it's made up of this NEMA 23 motor here, a 3D printed coupler that I designed, a 1/2" Acme threaded rod, and your lead screw nut, which I have right here. It's just a brass nut connected to this little housing that'll get mounted to the gantry. Very simple system. I chose the NEMA 23 motor because it was a little bit higher torque. It's a 200 ounce-inch motor. I got it off of eBay for about $12.50 plus shipping. It's a refurbished motor, but I think it's going to be plenty strong, and the price was right for this project. Now, one thing I would probably do differently next time is the motor that I have here has a smooth shaft. I would probably go with a notched shaft next time I did this build, because that way I can add a set screw, and I know that the rod is going to be fastened very, strongly to this motor. What I did with this coupler is I added the threads into the coupler itself to really lock in that Acme rod, and hopefully the tension of these 6 bolts here, or machine screws, lock that coupler on there without creating or allowing for any kind of slipping of the motor. We'll see. It may be a non-issue, but if it is an issue, I'd recommend going with a slotted shaft motor. Alright guys, we've got the main structure together now for the base of the CNC. I went ahead and lubed up the X-axis T-slot extrusion rails with this lubricant here. This is a Teflon lubricant that's a dry lubricant, so it's not like an oil or a 3-in-1 or something like that that can actually collect dirt and dust and particulate. Being dry, it allows you to create a really smooth surface for the wheels to roll on and the gantry to roll on like that without attracting dirt. So I highly recommend it. There was a little bit of stickiness to the gantry when I first assembled it, and as soon as I sprayed that Teflon dry lube on there, it went away, and the gantry, as you can see, moves really smoothly. So the next part that we have to do for the X-axis mechanism is attach this lead screw nut to the lower horizontal member. And I've got these T-slot connectors. Essentially what they are is they're 90-degree T-slot connectors. They go in the slots of the T-slot to hold one piece of T-slot to another piece of T-slot. What I'm going to use this for is a adjustable way of centering that nut and securing that nut to that lower T-slot horizontal cross member there. And the way that I'm doing that is I drilled holes on either side of this piece of tubing that I made, and I have set screws in those T-slot connectors, and I have one on each side, and with an Allen key I can loosen them up here and slide them in place just like that. And here you can see it a little bit better. We've just got a set screw holding that connector in the slot of the T-slot, and then there's a set screw on each side that locks it into the holes that I drilled in the tubing. Really simple system that I think will be effective. We'll find out. Okay, now that we've got the lead screw nut for the X-axis secure, there's only one step left to finish up the base in the X-axis, and that is to install the bed. This process is probably the simplest step of the entire process. What you're going to want to do is pre-drill 6 mounting holes in your small T-slot extrusion rails, which I've already done here. We're going to take the bed, slip it right in here. And one thing you'll want to keep in mind is when you're pre-drilling the holes for your 1/4-20 inserts for the clamps that go into this board, you want to make sure that they're located out of the way of those rails. We don't want them interfering with the mounting rails at all, otherwise the bed will be unlevel. After that, you just take 6 wood screws, any kind will work, and screw up from the bottom into the bed. Make sure that your screws are not too long so that if the router digs into the wasteboard a little bit, it won't hit your screws and you'll be good to go. If you enjoyed this video, please check out my Patreon page. I'll have more information about the parts and where to purchase them. And as soon as I can find a repository online to make the cut files and the 3D print files available, I'll post those on my Patreon page as well. So stay tuned for the next video, guys. Thank you.